Boron nitride is a heat and chemically resistant refractory compound of boron and nitrogen with the chemical formula Bn. It exists in various crystalline forms that are isoelectronic to a similarly structured carbon lattice. The hexagonal form corresponding to graphite is the most stable and soft among Bn polymorphs, and is therefore used as a lubricant and an additive to cosmetic products. The cubic variety analogous to diamond is called CBN. It is softer than diamond, but its thermal and chemical stability is superior. The rare wurtzite Bn modification is similar to lattice.The and may even be harder than the cubic form. Because of excellent thermal and chemical stability, boron nitride ceramics are traditionally used as parts of high-temperature equipment. Boron nitride has potential use in nanotechnology. Nanotubes of Bn can be produced that have a structure similar to that of carbon nanotubes, i.e., graphene sheets rolled on themselves, but the properties are very different. Structure. Boron nitride exists in multiple forms that differ in the arrangement of the boron and nitrogen atoms, giving rise to varying bulk properties of the material. Amorphous form. The amorphous form of boron nitride is non-crystalline, lacking any long-distance regularity in the arrangement of its atoms. It is analogous to amorphous carbon. All other forms of boron nitride are crystalline. Hexagonal form. The most stable crystalline form is the hexagonal one, also called HBN, alpha Bn, GBN, and graphitic boron nitride. Hexagonal boron nitride has a layered structure similar to graphite. Within each layer, boron and nitrogen atoms are bound by strong covalent bonds, whereas the layers are held together by weak van der Waals forces. The interlayer registry of these sheets differs, however, for the pattern seen for graphite, because the atoms are eclipsed, with boron atoms lying over and above nitrogen atoms. This registry reflects the polarity of the Bn bonds. Still, HBN and graphite are very close neighbors, and even the BC6 and hybrids have been synthesized where carbon substitutes for some BN atoms. Cubic form. Cubic boron nitride has a crystal structure analogous to that of diamond. Consistent with diamond being less stable than graphite, the cubic form is less stable than the hexagonal form, but the conversion rate between the two is negligible at room temperature, as it is for diamond. The cubic form has the sphalerite crystal structure, the same as that of diamond, and is also called beta-Bn or CBN. Wurtzite form. The wurtzite form of boron nitride has the same structure as lattice.The, a rare hexagonal polymorph of carbon. As in the cubic form, the boron and nitrogen atoms are grouped into tetrahedra, but in WBN the angles between neighboring tetrahedra are different. Properties. Physical sources: amorphous Bn, crystalline Bn, graphite, diamond. The partly ionic structure of Bn layers in HBN reduces covalency and electrical conductivity, whereas the interlayer interaction increases, resulting in higher hardness of HBN relative to graphite. The reduced electron delocalization in hexagonal Bn is also indicated by its absence of color and a large band gap. Very different bonding, strong covalent within the basal planes and weak between them, causes high anisotropy of most properties of HBN. For example, the hardness, electrical and thermal conductivity are much higher within the planes than perpendicular to them. On the contrary, the properties of CBN and WBN are more homogeneous and isotropic. Those materials are extremely hard, with the hardness stiffness of bulk CBN being slightly smaller and WBN even higher than that of diamond. Polycrystalline CBN with grain sizes on the order of 10 nanometers is also reported to have viscous hardness comparable or higher than diamond. Because of much better stability to heat and transition metals, CBN surpasses diamond in mechanical applications, such as machining steel. The thermal conductivity of BN is among the highest of all electric insulators. Boron nitride can be doped P-type with beryllium and N-type with boron, sulfur, silicon, or if co-doped with carbon and nitrogen. Both hexagonal and cubic BN are wide-gap semiconductors with a band gap energy corresponding to the UV region. If voltage is applied to HBN or CBN, then it emits UV light in the range 215 to 250 nanometers and therefore can potentially be used as light-emitting diodes or lasers. Little is known on melting behavior of boron nitride. It sublimates at 2973 degrees Celsius at normal pressure, releasing nitrogen gas and boron, but melts at elevated pressure. Thermal stability. Hexagonal and cubic BN show remarkable chemical and thermal stabilities. For example, HBN is stable to decomposition at temperatures up to 1000 degrees Celsius in air, 1400 degrees Celsius in vacuum, and 2800 degrees Celsius in an inert atmosphere. The reactivity of HBN and CBN is relatively similar, and the data for CBN are summarized in the table below. Thermal stability of CBN can be summarized as follows: in air or oxygen, B2O3 protective layer prevents further oxidation to 1300 degrees Celsius, no conversion to hexagonal form at 1400 degrees Celsius. In nitrogen, some conversion to HBN at 1525 degrees Celsius after 12H. In vacuum, conversion to HBN at 1550 to 1600 degrees Celsius. Chemical stability. Boron nitride is insoluble in the usual acids, but is soluble in alkaline molten salts and nitrides, such as lithium hydroxide, CoNaOH, sodium carbonate, sodium nitrate, lithium nitride, magnesium nitride, SeNO3N2, barium nitride, Al3BN2, which are therefore used to etch BN. Thermal conductivity. The theoretical thermal conductivity of hexagonal boron nitride nanoribbons can approach 1700 to 2000 with, which has the same order of magnitude as the experimental measured value for graphene, and can be comparable to the theoretical calculations for graphene nanoribbons. Moreover, the thermal transport in the BNNRs is anisotropic. The thermal conductivity of zigzag-edged BNNRs is about 20% larger than that of armchair-edged nanoribbons at room temperature. Natural occurrence. In 2009, a naturally occurring boron nitride mineral was reported in Tibet. The substance was found in dispersed micron-sized inclusions of chingsongite in chromium-rich rocks in Tibet. In 2013, the International Mineralogical Association affirmed the mineral and the name. Synthesis, preparation and reactivity of hexagonal BN boron nitride is produced synthetically. Hexagonal boron nitride is obtained by the reacting boron trioxide or boric acid 3 with ammonia or urea 2 in a nitrogen atmosphere. B2O3 plus 2NH32 BN plus 3H2O B3 plus NH3 BN plus 3H2O B2O3 plus CO2 2 BN plus CO2 plus 2H2O. B2O3 plus 3 calcium boride plus 10 N220 Bn plus 3 calcium oxide. The resulting disordered boron nitride contains 92 to 95% Bn and 5 to 8% B2O3. The remaining B2O3 can be evaporated in a second step at temperatures in GT 1500 degrees Celsius in order to achieve Bn concentration and GT 98%. Such annealing also crystallizes Bn, the size of the crystallites increasing with the annealing temperature. HBN parts can be fabricated inexpensively by hot pressing with subsequent machining. The parts are made from boron nitride powders, adding boron oxide for better compressibility. Thin films of boron nitride can be obtained by chemical vapor deposition from boron trichloride and nitrogen precursors. Combustion of boron powder in nitrogen plasma at 5500 degrees Celsius yields ultrafine boron nitride used for lubricants and toners. Boron nitride reacts with iodine fluoride in trichlorofluoromethane at -30 degrees Celsius to produce an extremely sensitive contact explosive Ni3. In low yield, boron nitride reacts with nitrides of alkali metals and lanthanides to form nitride-operate compounds. For example, lithium nitride plus BN.Li3 BN2 intercalation of hexagonal Bn similar to graphite. Various molecules, such as NH3 or alkali metals, can be intercalated into hexagonal boron nitride, that is inserted between its layers. Both experiment and theory suggest the intercalation is much more difficult for Bn than for graphite. Preparation of cubic Bn. Synthesis of CBN uses same methods as that of diamond. Cubic boron nitride is produced by treating hexagonal boron nitride at high pressure and temperature, much as synthetic diamond is produced from graphite. Direct conversion of hexagonal boron nitride to the cubic form has been observed at pressures between 5 and 18 gigapascals and temperatures between 1730 and 3230 degrees Celsius. That is similar parameters as for direct graphite-diamond conversion. The addition of a small amount of boron oxide can lower the required pressure to 47 gigapascals and temperature to 1500 degrees Celsius. As in diamond synthesis, to further reduce the conversion pressures and temperatures, a catalyst is added, such as lithium, potassium, or magnesium. The nitrides, the fluoronitrides, water with ammonium compounds, or hydrazine. Other industrial synthesis methods, again borrowed from diamond growth, use crystal growth in a temperature gradient, or explosive shockwave. The shockwave method is used to produce material called heterodiamond, a superhard compound of boron, carbon, and nitrogen. Low-pressure deposition of thin films of cubic boron nitride is possible. As in diamond growth, the major problem is to suppress the growth of hexagonal phases, whereas in diamond growth this is achieved by adding hydrogen gas. Boron trifluoride is used for CBN, ion beam deposition, plasma-enhanced chemical vapor deposition, pulsed laser deposition, reactive sputtering, and other physical vapor deposition methods are used as well. Preparation of wurtzite Bn. Wurtzite Bn can be obtained via static high-pressure or dynamic shock methods. The limits of its stability are not well defined. Both CBN and WBN are formed by compressing HBN, but formation of WBN occurs at much lower temperatures, close to 1700 degrees Celsius. production statistics, whereas the production and consumption figures for the raw materials used for BN synthesis, namely boric acid and boron trioxide, are well known. The corresponding numbers for the boron nitride are not listed in statistical reports. An estimate for the 1999 world production is 300 to 350 metric tons. The major producers and consumers of BN are located in the United States, Japan, China and Germany. In 2000, prices varied from about $75 per kilogram to $120 per kilogram for standard industrial quality HBN and were about up to $200–400 per kilogram for high purity BN grades. Applications: hexagonal BN. Hexagonal BN is the most widely used polymorph. It is a good lubricant at both low and high temperatures. HBN lubricant is particularly useful when the electrical conductivity or chemical reactivity of graphite would be problematic. Another advantage of HBN over graphite is that its lubricity does not require water or gas molecules trapped between the layers. Therefore, HBN lubricants can be used even in vacuum, e.g. in space applications. The lubricating properties of fine-grained HBN are used in cosmetics, paints, dental cements, and pencil leads. Hexagonal BN was first used in cosmetics around 1940 in Japan. However, because of its high price, HBN was soon abandoned for this application. Its use was revitalized in the late 1990s with the optimization HBN production processes, and currently HBN is used by nearly all leading producers of cosmetic products for foundations, makeup, eyeshadows, blushes, kohl pencils, lipsticks and other skincare products. Because of its excellent thermal and chemical stability, boron nitride ceramics are traditionally used as parts of high-temperature equipment. HBN can be included in ceramics, alloys, resins, plastics, rubbers, and other materials, giving them self-lubricating properties. Such materials are suitable for construction of e.g. bearings and in steel making. Plastics filled with BN have less thermal expansion as well as higher thermal conductivity and electrical resistivity. Due to its excellent dielectric and thermal properties, BN is used in electronics e.g. as a substrate for semiconductors, microwave transparent windows, and as a structural material for seals. Hexagonal BN is used in xerographic process and laser printers as a charge leakage barrier layer of the photo drum. In the automotive industry, HBN mixed with a binder is used for sealing oxygen sensors, which provide feedback for adjusting fuel flow. The binder utilizes the unique temperature stability and insulating properties of HBN. Parts can be made by hot pressing from 4 commercial grades of HBN. Grade HBN contains a boron oxide binder. It is usable up to 550 to 850 degrees Celsius in oxidizing atmosphere and up to 1600 degrees Celsius in vacuum, but due to the boron oxide content is sensitive to water. Grade HBr uses a calcium borate binder and is usable at 1600 degrees Celsius. Grades HBC and HBT contain no binder and can be used up to 3000 degrees Celsius. Two-dimensional HBN has been shown to be an excellent proton conductor, yielding unexpectedly high proton transport rates. This high proton transport rate, combined with the high electrical resistance of HBN, may lead to important advances in research such as fuel cells and water electrolysis. HBN has been used since the mid-2000s as a bullet and bore lubricant in precision target rifle applications as an alternative to molybdenum disulfide coating, commonly referred to as moly. It is claimed to increase effective barrel life, increase intervals between bore cleaning, and decrease the deviation in point of impact between clean bore first shots and subsequent shots. Cubic boron nitride. Cubic boron nitride is widely used as an abrasive. Its usefulness arises from its insolubility in iron, nickel, and related alloys at high temperatures, whereas diamond is soluble in these metals to give carbides. Polycrystalline CBN abrasives are therefore used for machining steel, whereas diamond abrasives are preferred for aluminum alloys, ceramics, and stone. When in contact with oxygen at high temperatures, BN forms a passivation layer of boron oxide. Boron nitride binds well with metals, due to formation of interlayers of metal borides and nitrides. Materials with cubic boron nitride crystals are often used in the tool bits of cutting tools. For grinding applications, softer binders, e.g., resin-porous ceramics, and soft metals, are used. Ceramic binders can be used as well. Commercial products are known under names Boron and L-Bor or cubonite. Similar to diamond, the combination in CBN of highest thermal conductivity and electrical resistivity is ideal for heat spreaders. Contrary to diamond, large CBN pellets can be produced in a simple process of annealing CBN powders in nitrogen flow at temperatures slightly below the BN decomposition temperature. This ability of CBN and HBN powders to fuse allows cheap production of large BN parts. As cubic boron nitride consists of light atoms and is very robust chemically and mechanically, it is one of the popular materials for X-ray membranes. Low mass results in small X-ray absorption, and good mechanical properties allow usage of thin membranes, thus further reducing the absorption. Amorphous boron nitride. Layers of amorphous boron nitride are used in some semiconductor devices, e.g., NIMSoffice. They can be prepared by chemical decomposition of trichloroborosine with cesium, or by thermal chemical vapor deposition methods. Thermal CVD can be also used for deposition of HBN layers, or at high temperatures, CBN. Other forms of boron nitride. Boron nitride nanomesh. Boron nitride nanomesh is a nanostructured two-dimensional material. It consists of a single BN layer, which forms by self-assembly a highly regular mesh after high-temperature exposure of a clean rhodium or ruthenium surface to borosine under ultra-high vacuum. The nanomesh looks like an assembly of hexagonal pores. The distance between two pore centers is 3.2 nanometers and the pore diameter is tilde 2 nanometers. Other terms for this material are boronitrine or white graphene. The boron nitride nanomesh is not only stable to decomposition under vacuum, air and some liquids, but also up to temperatures of 800 degrees Celsius. In addition, it shows the extraordinary ability to trap molecules and metallic clusters which have similar sizes to the nanomesh pores, forming a well-ordered array. These characteristics promise interesting applications of the nanomesh in areas like catalysis, surface functionalization, spintronics, quantum computing and data storage media like hard drives. Boron nitride nanotubes. Boron nitride nanotubes were predicted in 1994 and experimentally discovered in 1995. They can be imagined as a rolled-up sheet of boron nitride. Structurally, it is a close analog of the carbon nanotube, namely a long cylinder with diameter of several to 100 nanometers and length of many micrometers, except carbon atoms are alternately substituted by nitrogen and boron atoms. However, the properties of BN nanotubes are very different. Whereas carbon nanotubes can be metallic or semiconducting depending on the rolling direction and radius, a BN nanotube is an electrical insulator with a band gap of 5.5 electron volts, basically independent of tube chirality and morphology. In addition, a layered BN structure is much more thermally and chemically stable than graphitic carbon structure. Composites containing BN. Addition of boron nitride to silicon nitride ceramics improves the thermal shock resistance of the resulting material. For the same purpose, BN is added also to silicon nitride alumina and titanium nitride alumina of ceramics. Other materials being reinforced with BN include alumina and zirconia, borosilicate glasses, glass ceramics, enamels, and composite ceramics with titanium boride, boron nitride, titanium boride, aluminium nitride, boron nitride, and silicon carbide boron nitride composition. Health issues. Boron nitride is reported to show weak fibrogenic activity, and to cause pneumoconeurosis when inhaled in particulate form. The maximum concentration recommended for nitrides of non-metals is 10 mg per cubic meter for BN and 4 for aluminium nitride or zirconium nitride.